Greetings, everyone. Today we're going to learn how to solve the chem243 experiment 3 email assignment. And to get started, we're going to first have to go to Moodle. And at Moodle, we find the email questions and submission area here, section 5. The email questions for experiments 3 and 4 are here. And here is the email question for experiment 3. Questions underneath a graph. We have to use this graph, and you're going to need your student number. I posted your student number right beside your syllabus quiz submission. So even if I gave you a student number before, this new number supersedes that. I am going to do this assignment based on a fictitious student. Here's the assignment, and I'm going to be student 86. Doesn't exist on your assignment. And student 86 has the following values. A is equal to 37.5 milliliters. And B is equal to 51.2 milliliters. So how are we going to start this question where we have to use a graph whose x-axis requires us to know the mole fraction in order to predict either the temperature of a liquid, that's this curve, liquid curve, or the temperature of a vapor above a liquid, that's this curve here. Both curves will be used in this assignment. So with those numbers, 37.5 milliliters representing the amount of methanol, and 51.2 milliliters representing the amount of water, how are we going to get to mole fraction? We can't use milliliters. Milliliter fraction is not the same as mole fraction, and milliliter fraction is meaningless. So our job, as you learned in your Chem 1 class and did thousands of times, is to go to moles and then go to mole fraction. So how are we going to get 37.5 milliliters of methanol to be moles? Well, we go to the Aldrich catalog, and I found on page 1752 of this edition, I believe the 2009 edition, there's actually about 3.5 pages of methanol. I expanded this region here over here. I only need this region because it has the data I need. The density, 0.791 grams per milliliter, and the formula weight, 32.04. And if we don't know formula weights, then we're in trouble. Those are grams per mole, and you will not be told that. 32.04 grams per mole. That's methanol, so let's work on that. We have 37.5 milliliters. We can't go to moles unless we have grams and then moles. That's a density conversion right there. I'm not memorizing equations. I'm just using units. I need to get rid of milliliters and make it grams so I can go from grams to moles. There are 0.791 grams. We looked it up. For every 1 milliliter. And we have to convert that to moles now. There's 1 mole for every 32.04 grams. We looked that up as well. And when we do the math, we get 0.9258 moles. Why did I keep one extra sig fig? Because this is not my final answer, and I don't want to have rounding errors. That's methanol. Water, we don't really have to do the research on water because it is my hopes that you know the density of water is 1 gram for every milliliter. We should know that for the rest of our lives. So many things are based on water. And there's 1 mole of water. You could do the periodic table, or you may have already done this so many times that you know it's 18.02, keeping an extra sig fig always when we want to. And when we work this out, that's going to be clearly more than 2 moles, 2.841 moles. And we can't use these numbers. I've seen students use these numbers on this graph and they say, oh, there's the moles of methanol. I'm going to use it. I'm going to go all the way over here, 0.9258, and do the graph. No, you got to use mole fraction. Mole fraction, the symbol is, it looks like an X, but it's called chi, spelled like the T, CHI. Now, the chi of methanol is the moles of methanol over the total moles. 0.9258 over 0.9258, which is the portion that's methanol, plus 2.841. And when you work out that fraction, it looks to be pretty close to a quarter. One over close to 4, and it comes out to 0.246. That is a final answer, so it's got the right number of sig figs. And what are the units? Waiting for an answer? Good answer. No answer. There are no units. That's the number we need to use on this graph, both in this email assignment and then when you do the email assignment again on the midterm exam, and most likely again on the final exam. Yes, this is important. So I need to go to 0.246 mole fraction of methanol. Notice the x-axis can be read this way. Mole fraction of methanol from 0 to 1, and mole fraction of water from 0 to 1 this way, because the total is always 1. 1 plus 0 is 1, 0 plus 1 is 1, 0.1 plus 0.9 is 1, etc. There's 0.2, there's 0.25, this is, sorry, 0.2 and 0.3, halfway is 0.25, which is real close to what we need here. Please make sure you bring a ruler to your midterm and your final. So I'm going to try on the screen to go right, starting here, and using a ruler all the way up to the liquid curve, because we're starting with a liquid mixture. Milliliters of methanol mixed with milliliters of water is a liquid mixture. And we're trying to go from the middle here all the way up to our curve. And apparently I forgot to put the pen on. Nice red pen. I do not want to move my graph. And we're moving our graph again because I don't know why. There. This may be an issue that I didn't anticipate. There we go. Nice straight line. Ha. Cheater. Okay. And it's just a hair left of halfway between 0.2 and 0.3, which is 0.25. This needs to make it up to the curve. All right, now we have to know a little chemistry. What happens to a liquid when you heat it? It creates more vapor. What temperature is this vapor? The vapor is exactly the same temperature as the liquid below it. So which way do we go on our curve? We're going to heat our liquid, and we're not going to create a vapor that's hotter than the liquid. That makes absolutely no sense. How could it get hotter than the liquid it comes from? The liquid is the same temperature as the vapor. And this is the same concept exactly as, what is the temperature of a mixture of ice and water? Answer, 0 degrees Celsius. You got solid and liquid in equilibrium, and until all of that solid is melted, the water will be at 0 degrees Celsius and the ice will be at 0 degrees Celsius. Same concept here, except you're talking about a liquid that's at a little over 85, and that's going to be the answer to one of our questions. And it's going to boil it. It's going to vaporize. Yeah, it's going to boil at 85. I'm going to continue with my red pen, make sure it's writing on the screen and not moving our graph. Straight across, then I didn't use the straight function using a ruler. Please use a ruler. And it made it nice and horizontal for me. Nice. Make sure you go to that there. That's important. And we're also going to do a reading of the temperature. And I don't think I can change the color of that, so I don't want to do that. We're going to do a reading of the temperature. We'll do our readings in yellow. All right, I got a new pen I'm trying to get used to here. Doesn't scratch my screen. All right, we're going and reading the temperature. And let's see, what do we have? 85. Let's see, 87 and a half's in the middle. 87's about right there. 86 is right there. 85.3 would be a decent estimate of that right there. So the answer to question A is, what is the mole fraction? Well, we did that. I could ask what the boiling point of this mixture is, and that wasn't asked. It's a fair question. Just graph reading 101. But right now, this mixture will start, it's boiling at 85.3. What happens to a liquid after you boil it? It undergoes evaporation. And this is the first time we're doing an evaporation, so I'll call it evaporation number 1. And when this vapor that you created hits a cool surface, what's going to happen is it's going to condense. And it'll condense with the same mole fraction. Of course, you're condensing a vapor, and every molecule that's the vapor will condense down back to a liquid. And there we go. And that, what we just accomplished there was condensation number 1. I'll write it over here and then move it. Condensation number 1. And shrink it a little bit right there. And what we've done right there in the process of evaporation and condensation is what's called a theoretical plate. That's the answer to question 2. It's a cycle of evaporation followed by condensation. And our goal is to prove that the more theoretical plates you get, the higher the percentage of methanol. We call methanol in this example the more volatile chemical, or you could say more volatile component, MVC. The definition of MVC is asked for on both the midterm and most likely the final. And how do I know methanol is more volatile? Well, a solution that was 100% methanol has a boiling point of a little over 66 or 65. 67 and a half there. I'd say close to 67. Okay, and a pure solution of water, you already know, but 100% water means you're over here. And are you surprised that's up at 100 degrees Celsius? That is a less volatile chemical. Water with a boiling point of 100 creates less vapor than methanol with a boiling point of 67. So the more volatile chemical, are you surprised our mole fraction went from being 0.246 at our beginning to our new liquid here after one theoretical plate. This is TP number 1. Theoretical plate, TP, is now more than 0.3, 0.4, 0.5. It's about 0.6. You went from something that was 25% pure to 60% pure after one theoretical plate. This question that's coming up, what will be the mole fraction of methanol after 2 theoretical plates of distillation? Question 3. Well, let's do our second theoretical plate. We have to evaporate our new liquid. Does not like me being on the bottom of the screen for some reason. Okay. Horizontal line. And horizontal line here. And pretty good. Maybe move it over a hair. I don't think it'll let me. No. We're real close though, as long as I don't move the graph again. And we want to know a couple things about this new liquid. This is evap number 2. Evaporation number 2. And this was condense number 2. And what is the combination of those two things called? You guessed it, theoretical plate number 2. And our stuff is a lot more pure than it used to be, isn't it? The 2 remaining questions that need to be answered. Just a reminder, question 1 we answered here. Question 2, right by question 2. Question 3, what is the boiling point of the condensate after 2 theoretical plates? That involves us reading the graph from the condensate as a liquid. I hope we know that. Condensate's a liquid and its boiling point we're reading across here. Don't think I used a straight line. There we go. And that is just a hair above halfway. And halfway is 67.5. My answer to question 3 is right here. I'm going to say 68 degrees is my best estimate. That's the answer to question 3. And what will be that's the boiling, that's question 4. Oh, I did question 4. Boiling points, 4. Question 3, and read the graph differently. What will the mole fraction of methanol be after 2 theoretical plates of distillation? Theoretical plate number 1, theoretical plate number 2. What is the mole fraction right here? We're reading the graph to the x-axis, straight line. And let's see, that's 0.8, that's 0.9, halfway is 0.85. I'm going to go, it's not 8.6, that'd be a little closer, maybe 8.7. How's that? Answer to question 3. 0.87. And you got to tell me you know what you're talking about here by saying that's the mole fraction of water, of methanol, sorry, methanol. And that brings to a conclusion our solving of the email question for experiment 3. And we're supposed to submit it. It used to be submitted by email, and that is no longer the case. Email assignment answers are due by, it says by email. This is the old version. The new version doesn't say that anymore. I promise you. Let's go to the new version. I just edited it, that's why. Okay. At least I hope the new version doesn't say that anymore. Yeah, it says, but due by email still. Okay, I'm going to edit that. Oh, submit them to section 5 at Moodle. There's no, I'm just got to get rid of by email. I didn't do that. But that's it. And section 5 of Moodle's where you submit it, 11 p.m. due date of experiment 3. Check the due dates in the experiment 3 submission area, and then you know where to put it. And I hope this was helpful, and I'll see you in the lab.